Welcome, and let yourself settle into this moment, breathing slowly as we prepare to descend together into one of Earth's most mysterious realms. Tonight, we're going to explore the hidden world of whale communication, drifting through the deep ocean where enormous intelligent beings speak to one another across distances we can barely imagine. As you listen, allow the gentle rhythm of these words to carry you downward, deeper and deeper into relaxation, while we uncover the secrets of how whales talk, think, and feel in the vast blue darkness beneath the waves. Before we begin, if you enjoy falling asleep to these explorations of the natural world, consider subscribing to Gentle Sleep ASMR, and let's take a slow breath together before we dive beneath the surface. Imagine standing at the edge of the ocean on a calm evening, watching the sun sink below the horizon. The water stretches endlessly before you, its surface reflecting the dimming light in shades of violet and gold. Perhaps you've stood at such an edge yourself, feeling the salt breeze on your skin, hearing the rhythmic percussion of waves against the shore, sensing the immensity of what lies beyond the breakers. The smell of salt and seaweed fills your nostrils, that distinctive ocean scent that speaks of life and depth and ancient mysteries. The waves lap gently at the sand or rocks, each one whispering secrets in a language older than humanity. Beneath that gentle surface lies a world utterly different from the one we know on land, a realm so alien in its physics and sensory priorities that we might as well be contemplating another planet entirely. As you slip below the waterline in your mind, carried down on a slow breath, the light begins to fade almost immediately. This isn't gradual in the way twilight fades on land, where you have hours of dimming visibility, where you can watch colors deepen and shadows lengthen across familiar landscapes. In the ocean, light disappears with startling rapidity as you descend, eaten by the water itself. 10 meters down, the reds disappear from the spectrum, absorbed by the water molecules and dissolved salts. The vibrant crimson of a fish's scales becomes a muddy gray. A red coral reef loses its brilliant hue and appears brown or black. 20 meters deeper, and the oranges vanish, leaving only yellows, greens, and blues painting the underwater world. 30 meters down, you're surrounded by a twilight realm of blues and greens, everything else drained away, as if someone has applied a filter to reality itself, removing half the colors from existence. Go deeper still, to 50 meters, and even the greens begin to fade, leaving only shades of blue. The water pressure increases with every meter, 1 atmosphere of pressure for every 10 meters of depth, pushing in on your imagined body from all sides. At 100 meters, you're in a realm of deep blue twilight, the sun a dim memory far above, its light scattered and refracted through the water column, until only the faintest glow remains. 200 meters down, you've entered what oceanographers call the twilight zone, or the mesopelagic zone, where only the faintest traces of surface light penetrate, where most creatures have evolved enormous eyes to capture every available photon, or have given up on eyes altogether. Below 600 meters, you're in complete and utter darkness, where no sunlight has reached in all of Earth's history, where the concept of sight becomes nearly meaningless, where eyes evolved for detecting light have little purpose beyond perhaps sensing the bioluminescence of deep-sea creatures that create their own light through chemical reactions. But the ocean is not silent. And it is not empty of information. Far from it. In fact, the opposite is true. If you could hear as a whale hears, if you possessed the auditory sensitivity and range that evolution has granted these magnificent creatures, you would discover that this dark realm is alive with sound, filled with information flowing in all directions. A three-dimensional acoustic universe, communication travels not as light waves, but as pressure waves moving through water. The physics of sound underwater are fundamentally different from sound in air, and understanding these differences helps us appreciate why whales evolved to become such sophisticated acoustic communicators, why they invested so heavily in hearing and vocalization rather than vision and visual displays. Sound moves through the ocean at roughly 1,500 meters per second econd, though the exact speed varies depending on water temperature, salinity, and pressure. To put this in perspective, sound in air travels at about 343 meters per second econd at sea level, so sound underwater moves more than 4 times faster than in air, covering greater distances in less time. But speed is only part of the story. The more important factor is how far sound can travel before it's absorbed or scattered into inaudibility. In air, sound waves lose energy quickly. Shout across a canyon, and your voice might carry a kilometer or two before it fades into the background noise of wind and rustling leaves. In the ocean, particularly at low frequencies, sound can travel hundreds or even thousands of kilometers with relatively little loss of intensity. This difference arises from the physical properties of the medium itself. Water is about 800 times denser than air, and this density affects how sound propagates. When a sound is produced underwater, whether by a whale's vocalization or a ship's engine, or the rumbling of an underwater earthquake, it creates pressure waves that radiate outward in all directions, expanding spherically from the source. These waves move through the water, and as they do, several things happen. Some of the sound energy is absorbed, converted to heat through friction with water molecules. This absorption is frequency dependent, with higher frequencies being absorbed much more rapidly than lower frequencies. A high frequency click at 50 kHz might travel only a few hundred meters before it's absorbed, but a low frequency moan at 20 Hz can travel 1,000 kilometers or more. The sound waves also refract as they pass through water of different temperatures and densities. The ocean is not uniform. It's layered like a cake, with warmer, less dense water near the surface, colder, denser water at depth, and various thermoclines or temperature boundaries in between. When a sound wave crosses from one layer to another, it bends, changing direction, just as light bends when it passes from air into water. This refraction can focus sound waves, concentrating them in particular layers, or it can scatter them, dispersing the energy over a wider area, where light can travel only dozens, or perhaps a couple hundred meters, before being absorbed by water particles and dissolved salts, before being scattered by suspended sediment and plankton. Sound can journey for hundreds of kilometers, sometimes thousands, creating invisible highways of information that span entire ocean basins. These acoustic highways are not equally available at all depths. To reach a particular layer in the deep ocean, typically at depths between 800 and 1,200 meters, where the combination of temperature and pressure creates what's called the SOFAR channel, which stands for sound fixing and ranging channel. In this layer, sound waves that try to travel upward or downward are refracted back toward the channel center, effectively trapping the sound and allowing it to propagate horizontally with minimal loss. Think of it as an acoustic waveguide, a tube of water through which sound can travel vast distances. Underwater explosions detected in the Sofar Channel have been recorded on the opposite side of entire oceans, traveling more than 16,000 kilometers. This is the world that whales evolved to inhabit, a world where ears became far more valuable than eyes, where voices became more essential than visual displays, where the primary sense for understanding one's surroundings shifted from sight to sound. To understand whale communication, we must first understand this fundamental shift in sensory priorities, this reimagining of how to perceive and interact with the world. On land, we humans are primarily visual creatures, and this shapes everything about how we experience reality. We read facial expressions to understand emotions. We navigate by landmarks we can see. We choose our mates based partly on what they look like, partly on visual displays of status and health. Our world is painted in light and color, in textures visible to the eye. But descend into the ocean's depths, and all of that becomes irrelevant, useless. Evolutionary baggage. You could have the most beautiful coloring in the animal kingdom. Brilliant reds and oranges and yellows, intricate patterns that would dazzle any observer. But if no one can see you in the darkness, if the wavelengths of light needed to reveal those colors don't penetrate to your depth, what purpose does it serve? You could have the keenest eyes capable of resolving fine details, of distinguishing subtle shades. But if there is no light to reflect off objects, if photons are so scarce that even the most sensitive retina cannot form an image, those eyes cannot build a picture of your surroundings. Vision fails in the deep ocean, and animals that live there must rely on other senses. Whales, over the course of roughly 50 million years, solved this problem by becoming acoustic specialists, by developing sensory and communication systems based on sound rather than light. Their ancestors, small four-legged mammals that looked something like modern deer or wolves, lived on land during the Eocene epoch. These early cetaceans, creatures like Pac, A, C, Tus, and Ambulocetus, were semi-aquatic, spending time both on land and in shallow coastal waters. They waded into the shallows to feed, catching fish and other aquatic prey, then returned to land to rest and rear their young. Over millions of years, they spent more and more time in the water, their bodies adapting to aquatic life. Their legs shortened and transformed into flippers. Their nostrils migrated from the tip of the snout to the top of the head, becoming blowholes. Their bodies became streamlined, torpedo-shaped for efficient swimming. They lost their external ears, which would have created drag in the water. And crucially, their sensory systems transformed as their bodies changed, becoming more and more adapted for life in the water, for diving to greater depths and spending longer periods submerged. The emphasis in their sensory world shifted from sight to sound, from eyes to ears, from visual communication to acoustic conversation. This was not a simple change. not just a matter of using one sense more and another less. It was a profound reorganization of how these animals perceived and interacted with their world, how they understood their place in space, how they recognized individuals and maintained social bonds, how they found food and avoided danger. It required changes, not just to the ears, but to the brain, to the cognitive systems that process sensory information and extract meaning from it. Think about how sound works in your daily life, how you use it, what information it provides. You might call to a friend across a park, and they hear you perhaps 50 meters away, if conditions are good, if there is no traffic noise or other interference. Their ears pick up the pressure waves created by your vocal cords, and their brain processes those waves, recognizing the pattern as your voice, extracting the meaning from the words you've spoken. Shout from a mountaintop, and your voice might carry a kilometer, echoing off distant peaks, fading gradually into the background hiss of wind through trees. But in the ocean, a whale's call can travel not just kilometers, but hundreds or thousands of kilometers under the right conditions. A blue whale calling off the coast of California can be heard by another blue whale near Hawaii, more than 4,000 kilometers away, if the conditions are ideal and both whales are positioned correctly in the water column. The ocean's density and temperature structure create these acoustic channels we've mentioned. Layers where sound waves can travel enormous distances with relatively little energy loss. Whales learn to exploit these channels over evolutionary time, developing behaviors and anatomies that allow them to position themselves at specific depths when they want their voices to travel far, using the ocean itself as a kind of natural amplifier and transmission system. When a blue whale wants to call across vast distances, it typically positions itself at a depth between 15 and 30 meters, right at the interface between the warm surface layer and the cooler water below. At this depth, the sound waves it produces enter the SOFAR channel and can propagate horizontally for hundreds of kilometers before dissipating. The physics of this are worth considering as we relax deeper into this exploration. As our breathing slows and our bodies become heavier against whatever surface supports us. Water is much denser than air, roughly 800 times denser, and that density affects how sound propagates in multiple ways. When a whale produces a vocalization, tightening muscles around air-filled structures in its head or throat, it creates pressure waves that radiate outward in all directions, like ripples from a stone dropped in a pond, but in 3 dimensions rather than 2. These waves move through the water, their pressure peaks and troughs alternating as they travel, carrying information about the source of the sound. The waves bounce off the surface of the ocean, reflect off the seafloor, refract through temperature gradients, where warm and cold water meet, and spread across vast distances. In the deep ocean, there is that layer we mentioned, the SOFAR channel, which sits at depths where the water temperature and pressure create a kind of acoustic waveguide. The temperature of the ocean generally decreases with depth, but the pressure increases. These 2 factors have opposite effects on sound speed. Increasing temperature makes sound travel faster, while increasing pressure also makes sound travel faster. Near the surface, temperature is the dominant factor, so as you descend and temperature drops, sound speed decreases. But at greater depths, pressure becomes more important. And even though temperature continues to drop, the sound speed starts increasing again because of the pressure effect. The minimum sound speed occurs at the depth where these effects balance, typically between 800 and 1200 meters. And this minimum creates a sound channel. Sounds that enter this channel, that are produced at or near the depth of minimum sound speed, can travel with minimal loss, because whenever they try to escape upward or downward, they're refracted back toward the channel center. Blue whales appear to have discovered this channel over evolutionary time and use it regularly, though they don't dive to the channel depth itself. Instead, they position themselves at shallow depths, and the geometry of sound propagation ensures that some of their acoustic energy enters the channel and travels vast distances. This is one of the many elegant solutions that evolution has found to the problem of long-distance communication in the ocean. The whales don't need to understand the physics consciously. They simply need to produce sounds at the right depth and frequency, and natural selection has favored individuals whose behavior and anatomy allowed effective long-range communication. Like the gradual dimming of light as you drift towards sleep, like the gentle fading of the day's concerns as relaxation deepens, we're descending deeper into this acoustic realm, and you might notice your breathing has slowed even further. Your body has melted into whatever surface supports you. Your mind has drifted away from the ordinary concerns of daily life. The whale's world is becoming more vivid, more present, more real, as our world of schedules and obligations fades into the background. This is natural. This is the gentle pull of learning, combined with the soft embrace of approaching rest. The mind engaged just enough to stay focused on these soothing words, but not so engaged that sleep cannot arrive. Whales are not a single type of animal, but rather a diverse group of species that fall into two main categories, two suborders that diverged from each other tens of millions of years ago, and have since evolved in somewhat different directions. There are the toothed whales, called odon, two seats, which include sperm whales, orcas, dolphins, porpoises, narwhals, belugas, and beaked whales. These are predators with teeth, sometimes hundreds of teeth lining their jaws, and they hunt fish, squid, octopus, and sometimes other marine mammals. They're active hunters, pursuing individual prey items, and many of them hunt at great depths or in complete darkness, relying on echolocation to find their food. Then there are the baleen whales, called Tige seats, which include blue whales, humpback whales, fin whales, right whales, gray whales, bowhead whales, and minke whales. Instead of teeth, these giants have baleen plates, long, flexible structures made of keratin, the same material as our fingernails and hair. These plates hang from their upper jaws like curtains, sometimes several hundred plates on each side of the mouth. The inner edges of the plates are frayed into bristles, creating a filter. When a baleen whale feeds, it takes in an enormous mouthful of water-containing prey, then uses its tongue to push the water out through the baleen. The prey, typically small schooling fish or tiny shrimp, like animals called krill, are trapped by the baleen filter, and the whale swallows them. A single blue whale can consume 6 tons of krill per Dalton Y during the feeding season. Both groups are highly vocal, but they use sound in different ways and produce it through different mechanisms, different anatomical structures that have evolved to serve their particular needs. The toothed whales are masters of echolocation, a form of biological sonar. They send out rapid clicks, sometimes hundreds of clicks per second econd, and listen to the echoes that bounce back from objects in the environment. By analyzing these echoes, measuring the time delay between click and echo, detecting the frequency shifts caused by relative motion, and comparing what their left and right ears hear, they can build a detailed acoustic picture of their surroundings. A dolphin hunting at night, in water murky with sediment, can detect a fish from hundreds of meters away, determine its size, shape, and speed, distinguish it from rocks or seaweed, and track it through complete darkness with extraordinary precision. Some researchers believe that echolocation may provide such detailed information that toothed whales can essentially see with sound, perceiving the internal structure of prey animals, distinguishing a healthy fish from a diseased one, even detecting the pregnancy of another cetacean. Their social communication, separate from echolocation, involves whistles, pulsed calls, and other vocalizations that help them coordinate hunts, maintain group cohesion, establish and maintain social hierarchies, and identify one another as individuals. Each bottlenose dolphin, for instance, develops a unique signature whistle, essentially a name that it uses throughout its life, and that other dolphins use when referring to it. The baleen whales, generally speaking, do not echolocate in the same way. There is some evidence that bowhead whales may use low-frequency sounds for a form of passive acoustic sensing, detecting echoes from ice formations or the seafloor, but they don't have the sophisticated echolocation systems of toothed whales. Instead, baleen whales produce low-frequency calls, sometimes extraordinarily powerful ones, that serve primarily for communication rather than navigation. These calls can be songs lasting many minutes, moans that rumble through the ocean depths, groans and rumbles, and other vocalizations that travel across ocean basins, connecting whales that may be separated by hundreds of kilometers. As we settle more deeply into this exploration, feeling the weight of our bodies pulling us down toward rest, feeling each breath come slower and deeper than the last, we can begin to appreciate what an extraordinary achievement whale communication represents. These animals took the basic mammalian ability to vocalize, the simple production of sounds through vibrating tissues, and transformed it into something far more sophisticated, something that in some species approaches the complexity we associate with human language itself. They didn't just get louder or develop better hearing. They evolved entirely new anatomical structures for producing sound. They developed neural systems capable of learning complex vocal patterns from other individuals. They created cultural traditions of communication, dialects and songs that vary between populations and change over time. Before we can understand what whales are saying to one another, before we can appreciate the meaning and significance of their calls, we need to understand how they produce these remarkable sounds. So let's turn our attention now to the anatomy of whale voices, the biological machinery that allows these creatures to sing, click, and call in the dark ocean depths. When we humans speak, when we produce the words that carry our thoughts from one mind to another, we force air from our lungs up through our larynx, commonly called the voice box, a cartilaginous structure in our throat. Inside the larynx, two bands of tissue called vocal cords, or vocal folds, stretch across the airway. When we tighten muscles around the larynx, these cords come together, and as air from our lungs pushes past them, they vibrate, opening and closing rapidly, chopping the airstream into pulses. These pulses create sound waves, the raw material of speech. We then shape those sounds with our tongue, lips, teeth, and the cavity of our mouth, turning raw vibrations into the distinct sounds of speech, the vowels and consonants that combine to form words. It's a system that works well in air, where we can breathe and vocalize simultaneously, taking in oxygen while producing extended utterances, speaking for minutes at a time without running out of breath. But whales face a unique and significant challenge. They're mammals, just like us, breathing air through lungs, requiring oxygen to fuel their metabolism, exhaling carbon dioxide as waste. But they live underwater. They cannot breathe and vocalize at the same time in the way we can. They must hold their breath while diving, sometimes for many minutes, in the case of shallow diving species like humpbacks, sometimes for over an hour in the case of deep diving species like sperm whales and beaked whales. When a whale surfaces and exhales, producing the dramatic blow that we recognize as the spout, it's expelling air that has been in its lungs during the entire dive. Then it takes several quick breaths, refilling its lungs with fresh air, and dives again. During the dive, while submerged, it cannot access more air. So how do these animals produce sound without constantly exhaling precious air? How do they vocalize continuously while holding their breath, sometimes producing calls that last for minutes or even hours? Toothed whales solved this problem with an elegant and sophisticated adaptation. Instead of using vocal cords in a larynx down in their throat, they produce sounds using structures in their nasal passages, up near their blowholes at the top of their head. Air is moved between a series of air sacs, chambers that can be inflated and deflated by muscular control. And as the air passes through constricted passages between these sacs, it vibrates specialized structures called phonic lips. These lips, sometimes referred to in older scientific literature as monkey lips because of their appearance under microscopy, are tissue complexes that project into the nasal passage. They consist of connective tissue, fat, and muscle, shaped into structures that can vibrate at very high frequencies when air is forced past them under pressure. The genius of this system, the elegant solution to the problem of underwater vocalization, is that the air is recycled. It doesn't escape into the water as bubbles, which would not only waste the air but would also make it impossible to produce sustained vocalizations. Instead, the air moves back and forth between the sacs, driven by muscular contractions, vibrating the phonic lips each time it passes through, allowing the whale to produce sound continuously without needing to surface for more air. It's analogous to playing a trumpet with your nose while holding your breath, if you can imagine such a thing, except far more sophisticated and efficient. But the system is even more sophisticated than just recycling air and vibrating tissues. In front of the phonic lips, toothed whales have evolved a structure called the melon, a large rounded fatty organ in their forehead, prominent in dolphins and belugas, massive in sperm whales. This melon is not just a fatty deposit, not just insulation or stored energy. It's a complex acoustic lens composed of different types of lipids with different acoustic properties arranged in concentric layers. The inner core has different acoustic properties than the outer layers, creating a structure that can focus sound waves just as a glass lens focuses light waves. The melon acts like a focusing device, taking the sound produced by the phonic lips and concentrating it into a directional beam. Instead of radiating in all directions equally, the sound is projected forward, aimed like we might aim a flashlight beam. or a spotlight. When a dolphin or sperm whale produces echolocation, clicks for hunting or navigation, those clicks are highly directional, beamed forward in a tight cone, perhaps only 10 to 20 degrees wide. The animal can sweep its head back and forth, scanning the environment with sound just as we might scan a dark room with a flashlight, illuminating first one area, then another, building up a mental map of the surroundings. The melon's shape and composition can even be adjusted slightly by muscular control, by changing the tension in muscles surrounding the melon, allowing the whale to change how tightly it focuses sound, making the beam wider for scanning a large area or narrower for examining a specific target in detail. This level of control over acoustic output is remarkable, suggesting sophisticated neural processing and feedback systems. The sounds produced by toothed whales vary enormously depending on the species, the context, and the purpose. Orcas, those sleek black and white predators also known as killer whales, the largest members of the dolphin family, produce a rich and varied vocabulary of sounds. There are echolocation clicks, rapid-fire bursts, where each click lasts less than a millisecond, produced at rates of up to several hundred clicks per second econd, used for navigating through murky waters and hunting fish or marine mammals. These clicks are broadband, containing energy across a wide range of frequencies, which allows the whales to extract detailed information from the echoes. There are whistles, high-pitched frequency-modulated sounds that rise and fall in pitch like musical notes, ranging from about half a kilohertz up to 40 kilohertz, used primarily for close-range communication within the pod, for maintaining contact between individuals swimming near each other, for coordinating movements and activities. And there are pulsed calls, which to human ears sound like squeaks, screams, and squawks, rapid series of pulses that blend together into what we perceive as single sounds. These pulsed calls are the most variable and the most commonly produced sounds by orcas, and they form the foundation of Orca dialects, the family-specific vocal traditions that we'll explore in more depth later. Each pod of orcas has its own unique set of pulsed calls, typically 7 to 17 discrete call types that are produced frequently and serve as acoustic badges of pod identity. These calls can travel several kilometers underwater, allowing pod members to stay in acoustic contact even when they're spread out over large areas, hunting in different locations or resting in different bays. Sperm whales, those deep-diving giants with massive square heads that can comprise up to a third of their body length, produce some of the loudest biological sounds on Earth, clicks that can reach levels of 230 decibels, measured at the source. To put this in perspective, a rock concert might be 120 decibels, which is at the threshold of pain for human ears. A jet engine at close range is around 140 decibels. Sperm whale clicks are nearly 100 decibels louder than a jet engine, though the comparison is not quite direct because the decibel scales for air and water are referenced differently. Nonetheless, these are extraordinarily powerful sounds, among the most intense acoustic signals produced by any living creature. These clicks are produced using the same phonic lip mechanism as other toothed whales, air being forced between sacs and vibrating tissue structures. But sperm whales have evolved an extraordinary amplification and focusing system that makes their clicks uniquely powerful. Their enormous heads are filled with a substance called sperm, set, a waxy oil that was once incorrectly thought to be the whale's sperm, hence the unfortunate name. When whalers first cut open sperm whale heads and found this milky white substance, they assumed it was seminal fluid and named both the substance and the whale accordingly. We now know that sperm, set, has nothing to do with reproduction. Instead, it's part of an elaborate sound production and focusing system. The sperm, set, organ is enormous, sometimes containing several tons of this oil, and it acts as an acoustic resonator and amplifier. When the whale produces a click using its phonic lips, the sound wave travels forward through the sperm, set, which has acoustic properties that allow sound to propagate through it efficiently. At the front of the head, is an air sac called the frontal sac, and sound bounces off this sac, reflecting backward. The wave travels back through the sperm, set, bounces off another reflective surface at the rear of the head called the distal sac, and travels forward again. This back and forth bouncing creates a series of pulses, each one slightly delayed from the last, that combine to form the characteristic sperm whale click. A series of rapid pulses rather than a single sharp sound. The longer the sperm, set, organ, the greater the delay between pulses, and since larger whales have longer organs, the timing of these pulses can actually indicate the size of the individual whale, providing a kind of acoustic signature based on body dimensions. A smaller whale might have pulses separated by 2 or 3 milliseconds, while a large bull sperm whale might have pulses separated by 5 or 6 milliseconds. Other sperm whales listening to these clicks can potentially assess the size of the caller, gaining information about whether they're hearing from a large adult male, a smaller female, or a juvenile, all from the fine structure of the click. Now let's turn our attention to the baleen whales, those filter-feeding giants that include the largest animals ever to exist on Earth. Creatures so massive that a blue whale's tongue alone can weigh as much as an elephant. Creatures whose hearts are the size of small cars, whose blood vessels are so large that a human child could swim through the aorta. Baleen whales do not have the phonic lip system of their toothed cousins. They have a larynx, somewhat like ours, positioned in their throat, but it lacks vocal cords or vocal folds. The question of exactly how baleen whales produce sound puzzled scientists for many years, because the larynx seemed like the obvious source. But without vocal cords, the mechanism was unclear. Recent studies, using high-speed video, computer modeling, and even experiments with larynxes from deceased whales have begun to reveal the answer. In baleen whales, the arytenoid cartilages, small paired structures in the larynx, that in humans help position and tense the vocal cords, have evolved into elongated cylinders that fuse together to form a U-shaped structure spanning nearly the entire length of the larynx. This rigid, elongated structure likely serves to keep the airway open when these enormous animals need to move huge volumes of air in and out during their brief surface intervals. A blue whale, surfacing after a dive, exhales and inhales several tons of air in just a few seconds, creating the explosive blow that can be seen from several kilometers away. The airway needs to remain open and structurally sound during this rapid exchange of air. But this U-shaped structure also serves another function. It pushes against a large fatty cushion on the inside of the larynx, and when the whale forces air from its lungs past this cushion, the cushion begins to vibrate, much as our vocal cords vibrate when we speak. These vibrations produce sound waves, and because the structures involved are so large, the vibrations are slow, producing very low frequency sounds, the deep rumbles and moans that characterize baleen whale vocalizations. The sounds are then modified by the resonating chambers of the nasal passages, the sinuses, and possibly other structures in the head and throat, though the details are still being researched and debated by scientists. Like toothed whales, baleen whales appear to recycle air when producing sounds. The air doesn't escape into the water as bubbles during vocalization. Instead, it's moved back and forth within the respiratory system, allowing the whales to produce sustained sounds without needing to exhale continuously into the water. This is crucial because these whales spend most of their time submerged, surfacing only briefly to breathe, and if they had to exhale to vocalize, they would quickly run out of air and need to surface, which would be highly inefficient and would limit their ability to forage at depth or travel long distances underwater. The sounds that baleen whales produce are among the most impressive in the animal kingdom, not just for their volume, though some species are extraordinarily loud, but for their range, their complexity, their diversity, and their sheer power to travel across entire oceans, connecting individuals, separated by distances that would take humans days or weeks to traverse. Blue whales. Around 20 Hz for young people with good hearing, higher for older individuals or those with hearing damage. To put this in perspective, to help you understand just how low these frequencies are, the lowest note on a standard piano is about 27.5 Hz, a deep rumble that you feel as much as hear. Blue whale calls are often deeper than that, a profound bass rumble that resonates through the ocean, like distant thunder rolling across a plain, like the deep tremor of an earthquake felt through the ground. If you could hear these calls directly, if you could somehow experience them at their source frequency, they would be felt in your chest and bones, as much as heard with your ears, a physical presence, as much as a sound. These calls can last from 10 to 30 seconds, sometimes longer. Phrases of sound sustained for durations that would be impossible for a human singer without taking a breath. And they're produced at sound levels of around 188 to 192 decibels, measured at 1 meter from the whale, which makes them among the loudest animal vocalizations ever recorded. Perhaps the loudest, depending on how you measure and compare across species. The power of these calls, the sheer acoustic energy involved, is difficult for us to comprehend living as we do in air, where our loudest sounds are so much quieter. In air, a rock concert might reach 120 decibels, which is at the threshold of pain for human ears, loud enough to cause hearing damage with prolonged exposure. A jet engine at close range is around 140 decibels, painfully loud, requiring ear protection. Blue whales are producing sounds 50 decibels louder than a jet engine, but underwater, where the physics of sound are different, where the reference pressure is different, because sound travels so efficiently through water, with less energy loss than in air, and because blue whales call at such low frequencies, which travel farther with less absorption than high frequencies. These calls can be detected over distances exceeding 1,600 kilometers, 1,000 miles, sometimes even farther under ideal conditions. In the early 1990s, researchers using the United States Navy's underwater listening system, a network of hydrophones originally deployed to listen for Soviet submarines during the Cold War, detected blue whale calls that had traveled across entire ocean basins. A whale calling off the coast of California could theoretically be heard by another blue whale near Hawaii, more than 4,000 kilometers away, if both whales were positioned correctly in the water column, and if the acoustic path between them didn't encounter too many obstacles or regions of high absorption. The ocean becomes a vast acoustic network, with these enormous beings sending messages back and forth across distances that would take us days to traverse in a fast boat. Connections maintained across the vastness of the sea through sound alone. Humpback whales smaller than blue whales, but still impressively large, reaching lengths of 12 to 16 meters and weights of up to 40 tons, are perhaps the most famous whale vocalizers because of their songs. Complex and beautiful performances that have captured human imagination since they were first widely publicized in the 1970s. Unlike the relatively simple, repetitive calls of blue whales, humpback songs are elaborate, structured, and lengthy performances that can last for 30 minutes or more, sometimes continuing for hours as the whale repeats the song over and over, with only minor variations. Only male humpbacks produce these elaborate songs, and they do so primarily during the breeding season, when the whales have migrated from their feeding grounds in cold, productive waters to warmer tropical or subtropical breeding areas. This sex-specific and season-specific pattern led researchers to believe early on that the songs serve a role in mating, perhaps as displays of male fitness to females, allowing females to assess the quality of potential mates based on song complexity, duration, or some other acoustic feature. Or perhaps the songs serve as territorial signals to other males, acoustic announcements of presence and quality that help males establish and maintain position in a social hierarchy without the need for physical combat, or possibly both, with the songs serving multiple functions simultaneously. The songs themselves have a hierarchical structure that researchers describe using terms borrowed from music theory and linguistics. The smallest unit is a single sound, which might last a second or two. A moan, a cry, a groan, a chirp, a series of similar sounds, repeated in sequence, forms a phrase. The phrase might consist of 3 or 4 or 6 sounds, produced one after another with brief pauses between them. Phrases are repeated multiple times, anywhere from 2 to dozens of repetitions, to create a theme. A theme is this repeated pattern, recognizable as a distinct section of the song, and several themes strung together, sung in sequence, make up a song. The whale will sing through all the themes, reaching the end of the song, and then begin again at the beginning, repeating the entire sequence. The precision with which whales remember and reproduce these songs is remarkable, suggesting sophisticated cognitive abilities, advanced memory systems, and fine motor control over vocalization. All the male humpbacks in a particular region, in a specific breeding population, sing essentially the same song at any given time, with only minor individual variations, small improvisations or errors that don't fundamentally change the structure. This population, wide conformity to a single song type, is one of the most fascinating aspects of humpback whale acoustics and raises profound questions about social learning, cultural transmission, and what it means for a non-human species to share a cultural practice. But the song is not fixed or unchanging. It evolves gradually over the course of a breeding season, with small changes accumulating as singers modify their performances and other singers adopt those modifications. A phrase that appeared early in the season might be extended or shortened. New sounds might be added. The number of repetitions might change. The tempo might shift. These changes don't happen randomly or independently in each individual. Instead, all the singers in a population adopt the modifications, maintaining a kind of consensus about what the current song should sound like, what the correct version is. The sounds themselves span a remarkable range of frequencies and types. There are low-frequency moans and groans, some as low as 30 Hz, deep bass tones that travel far through the ocean. There are mid-frequency sounds, whoops and ahs, that sit in the range where human hearing is most sensitive, which is partly why humpback songs sound so accessible and musical to our ears. And there are high-frequency chirps and cries that can exceed 8,000 Hz, higher than the highest notes on a piano. Some sounds in the songs are pure tones, single frequencies held steady, producing a clean whistling or flute-like quality. Others are frequency modulated, sweeping up or down in pitch, like a siren or a musical glissando, creating a sense of movement and emotion. Some are loud, projected forcefully. Others are relatively quiet, almost intimate. The overall effect, when you listen to a humpback song, even played back at a speed and frequency that makes it audible to human ears, is strangely musical, hauntingly beautiful, with phrases that seem to rise and fall with emotional weight, even though we don't know what, if anything, they mean to the whales themselves. Listening to these songs, you might feel a connection across species, a sense that these animals are not so different from us, that they too have something they're trying to express through sound, some inner experience or motivation that finds voice in these elaborate acoustic displays. Whether humpback songs contain specific meanings, whether they convey detailed information about the singer's identity, or location or intentions, or whether they're more like music than language, more about expression than communication of specific content, remains a matter of scientific debate and ongoing research. This concludes the first major portion of our journey through the acoustic world of whales. Your body is growing heavier now, sinking deeper into rest. Your breathing slow and regular. Your mind drifting peacefully on these currents of information about sound and anatomy and the remarkable adaptations that allow whales to communicate in the deep ocean. When you're ready, we'll continue deeper still, exploring the actual languages of whales, the dialects and songs and click patterns that vary from population to population, culture to culture, revealing that whales have not just communication, but something approaching language itself. As we continue our journey into the acoustic realm of whales, let your awareness settle even more deeply into a state of peaceful receptivity, that sweet space between waking and sleeping, where information flows effortlessly and the mind rests while still gently engaged. We've explored how whales produce their remarkable vocalizations, the biological machinery and evolutionary adaptations that allow them to send sounds across vast ocean distances. Now we turn to perhaps the most fascinating aspect of whale communication: what they're actually saying to one another, how their vocalizations are structured, and what information they convey, and how different whale populations have developed their own unique ways of speaking, their own dialects, and songs and click patterns that mark them as belonging to specific cultures, specific lineages of social learning and tradition. Let's begin with the blue whales, those incomprehensibly large beings whose bodies can reach lengths of 30 meters. That's nearly 100 feet, and weights approaching 200 tons, heavier than 30 African elephants, heavier than any creature that has ever lived. Despite their enormous size, despite the fact that you could fit an entire school bus in a blue whale's mouth, these animals feed on some of the ocean's smallest prey, tiny shrimp, like crustaceans called krill, that measure only a few centimeters in length. Blue whales are found in all the world's oceans except the Arctic, roaming widely across deep offshore waters, diving to moderate depths to feed on dense concentrations of krill, surfacing to breathe and sometimes to rest at the surface between feeding bouts. But they're not a single unified population, not one great tribe of blue whales, roaming freely and interbreeding throughout the world's oceans. Instead, they're divided into distinct groups that inhabit different ocean basins, populations that rarely, if ever, encounter one another, separated by thousands of kilometers and by behavioral patterns that keep them in different regions. There are populations in the North Atlantic, the North Pacific, the Indian Ocean, the Southern Ocean around Antarctica, and various smaller populations in between. And remarkably, each of these populations has its own vocal signature, its own pattern of calls that differs from the calls produced by other populations. The most common blue whale vocalization, the sound that researchers hear most often when monitoring these whales with underwater microphones deployed on the seafloor or suspended in the water column, is a patterned series of low-frequency sounds that has been broken down by scientists into different call types, labeled with letters for convenience. The A call is a long duration, low-frequency pulse, a steady tone that might last 15 or 20 seconds, a sustained rumble at a frequency so low that it's felt as much as heard. The B call is another tonal call, a pure frequency held steady at a slightly different pitch from the A call. The C call is an upswept tone, a sound that starts at one frequency and rises to a higher frequency over its duration, that precedes B calls in some populations. The D call is a moderate duration downswept tone, falling in frequency as it progresses, sweeping from perhaps 90 Hz down to 40 Hz over the course of a second or two, like a descending whistle but pitched far below human hearing. Different populations produce different arrangements of these basic elements, combining them in different orders, emphasizing some calls and omitting others entirely, creating population-specific song types that are as distinctive as human regional accents or dialects. For example, Antarctic blue whales, those giants that feed in the cold, krill-rich waters around Antarctica during the southern summer, produce calls that last roughly 18 seconds and consist of 3 distinct segments. First, to raise a 9-second long tone at 27 Hz, a sustained bass note that rumbles through the deep ocean. This is followed by a 1-second downsweep to 19 Hz, a dropping tone that falls in frequency, and then another downsweep to 18 Hz, falling even lower, ending the phrase with a profound bass rumble that might travel hundreds of kilometers through the Antarctic waters. These three-part calls are repeated at regular intervals, sometimes for hours, creating a rhythmic pattern that becomes almost hypnotic when you listen to recordings played back at speeds that make them audible to human ears. Blue whales off Sri Lanka, swimming in the warm waters of the Indian Ocean, where the continental shelf drops away into deep offshore waters, produce a very different song pattern. Their calls consist of a 3-unit phrase that's structured quite differently from the Antarctic song. The first unit is a pulsive call, a series of rapid pulses rather than a smooth tone, ranging from about 20 to 43 Hz and lasting roughly 18 seconds. The second unit is a frequency-modulated upsweep, rising from 56 Hz to 72 Hz over about 14 seconds, creating a rising tone. The final unit is a long tone, lasting about 28 seconds, that sweeps from 108 Hz down to 105 Hz. These differences are substantial and consistent. A researcher listening to blue whale calls can identify which population the whales belong to based solely on the call structure. Blue whales in the Northeast Pacific, the population that feeds along the coast of California and Mexico, have their own distinct patterns as well. They produce regular sequences of calls that differ in both timing and frequency structure from both the Antarctic and Sri Lankan populations. And so it goes around the world, with each major population having its own acoustic signature, its own way of structuring these low-frequency vocalizations. The consistency within populations and the differences between them suggest that these call patterns are not genetically hardwired, but are instead learned, passed from one generation to the next through social transmission. Young blue whales, hearing the calls of adults in their population, learn to produce those same calls, acquiring their population's vocal tradition, much as human children acquire the language and accent of the community into which they're born. These geographic variations are thought to serve multiple functions, multiple purposes in the lives of these enormous, wide-ranging animals. The calls certainly help blue whales maintain contact with one another across the vast distances they roam, the hundreds of kilometers they might cover in a day's travel, the thousands of kilometers they traverse during their annual migrations between feeding and breeding areas. A blue whale feeding in one area might call out, projecting its voice into the deep sound channel, and another whale hundreds of kilometers away might respond, allowing them to track each other's general locations even when they're far beyond visual range, even when they're separated by distances so great that it would take days to swim from one to the other. The calls likely also play a role in mating and reproduction, helping whales find potential partners in the vastness of the ocean. For a species with low population density, where individuals are often separated by enormous distances, being able to advertise one's presence over ranges of hundreds or thousands of kilometers could be crucial for successful reproduction. Males might call to attract females, advertising their presence and perhaps their fitness through the power and consistency of their calls. Females might call to signal their receptivity or location, helping males find them in the vast acoustic space of the ocean. And the fact that each population has its own signature call pattern might help whales identify which population a calling individual belongs to, potentially reducing interbreeding between populations that have adapted to different regions, different prey distributions, different environmental conditions. One particularly intriguing discovery about blue whale calls, a finding that has puzzled researchers since it was first documented, is that they've been getting deeper over time, shifting downward in frequency in a gradual but measurable way. Recordings from the 1960s, when scientists first began systematically recording whale vocalizations using hydrophones, show blue whale calls at higher frequencies than recordings from the 1980s. Recordings from the 1980s show calls at higher frequencies than recordings from the 2000s. This trend has been documented in multiple populations around the world, suggesting it's not a local phenomenon, but something happening globally across the species. The frequency has been dropping by roughly 0.1 to 0.5 Hz per year depending on the population, which might not sound like much, but over 40 or 50 years, it adds up to a significant shift. No one knows for certain why this is happening, though several theories have been proposed and debated in scientific literature. One suggestion is that as blue whale populations slowly recover from the devastation of commercial whaling, which killed hundreds of thousands of blue whales in the 20th century and drove them to the brink of extinction, there are more whales in the ocean now than there were a few decades ago. With more whales calling, there more acoustic competition, more overlap between different individuals' calls. Deeper calls, lower in frequency, travel farther with less absorption, and might be more effective at long-distance communication in this more crowded acoustic environment. Another possibility is that the calls are shifting in response to increasing ocean noise from shipping, though if that were the case, you might expect calls to get higher in frequency rather than lower, since higher frequencies would stand out more against the low-frequency rumble of ship engines. The mystery of the deepening calls reminds us how much we still have to learn about these animals and their acoustic lives. How many questions remain unanswered despite decades of research. From the simple, powerful calls of blue whales, let's turn now to the humpback whales, whose songs represent perhaps the most complex vocal displays in the entire animal kingdom outside of human language, and possibly birdsong in species like nightingales and mockingbirds. We've already discussed the basic structure of humpback songs, the hierarchical organization from units to phrases to themes to songs, but the true marvel, the aspect that has captivated researchers and inspired countless studies, lies in how these songs change over time and how those changes spread through populations in patterns that resemble the cultural evolution of human traditions. Each year, at the beginning of the breeding season, when male humpbacks gather in warm tropical waters to sing and compete for mating opportunities, they all sing essentially the same song, the song that had evolved by the end of the previous breeding season. But as the season progresses, as weeks turn into months, and the whales continue to sing day after day, a theme that appeared early in the season might be modified, with sounds added or removed, with the number of repetitions increased or decreased. New sounds might be introduced, novel vocalizations that hadn't appeared in previous years. The tempo might shift slightly, speeding up or slowing down. The order of themes might be rearranged. These changes don't happen randomly. with each individual whale inventing his own modifications independently. Instead, to reach a remarkable degree of coordination and conformity. When one whale introduces a modification that other whales adopt, the change spreads through the population, and soon all the singers are producing the new version. This process has been termed cultural evolution because the songs are passed from whale to whale through social learning rather than genetic inheritance. And they change over time in ways that parallel how human cultural traditions evolve, how languages change, how musical styles develop and spread. By the end of a breeding season, the song might be substantially different from how it began, with new themes added, old themes dropped or modified, the overall structure altered. The next year, when the whales return to the breeding grounds, after spending months feeding in distant cold waters, they pick up where they left off, singing the song as it existed at the end of the previous season and continuing to evolve it. But humpbacks occasionally undergo something even more dramatic than this gradual evolution, something that researchers call a song revolution. In a revolution, the entire song is suddenly replaced by a completely different song, usually one that originates from a neighboring population. The old song, which might have been sung for years and evolved gradually through countless subtle changes, disappears and is replaced wholesale by a novel song structure. The first documented song revolution occurred in 1996 and 1997. When the song sung by humpback whales in eastern Australia in the Pacific Ocean was rapidly replaced by the song from the Western Australian population, from the Indian Ocean. These two populations breed in different ocean basins, thousands of kilometers apart, but they feed in overlapping areas in Antarctic waters during the summer months. And it's thought that whales from the two populations encountered one another on the feeding grounds or along migration routes. Western Australian males, singing their population's song, were heard by Eastern Australian males, who began to learn and adopt the foreign song. Within about 2 years, the transition was complete. The old Eastern Australian song had vanished, and the new Western Australian song had taken over completely, sung by all the males in the population. This is extraordinary when you think about it. Imagine if everyone in the United States suddenly switched from speaking English to speaking French, not because of conquest or political change, but simply because French speakers arrived, and American speakers decided French sounded better. That's roughly analogous to what happened with these humpback populations. Since that initial observation, researchers have documented this pattern spreading eastward across the South Pacific in a kind of cultural wave. The Western Australian song moved to Eastern Australia, then to New Caledonia, then to Tonga, then to American Samoa, then to the Cook Islands, and eventually to French Polynesia, traveling roughly 10,000 kilometers across multiple breeding populations. Over the course of about each population adopted the song from its western neighbor, modified it slightly, and then passed it on to its eastern neighbor. More recently, scientists have found evidence that songs continue spreading eastward from French Polynesia to the breeding grounds off Ecuador and Colombia, another 8,000 kilometers across the Pacific, suggesting that this cultural transmission might eventually encircle the entire southern hemisphere. The mechanism by which songs spread is thought to involve whales from different populations encountering one another on shared feeding grounds or along migration routes, hearing foreign songs and learning them. Humpbacks are vocal learners, capable of imitating complex sound patterns they hear from other individuals, and males seem particularly attuned to novel songs, perhaps because novelty itself is attractive, perhaps because song complexity or novelty serves as a signal of cognitive ability or other qualities females find attractive. A male who can learn a complex new song and reproduce it accurately might be demonstrating mental flexibility and learning ability that translate to other fitness-related traits. The most exciting recent research on humpback whale songs, work published in 2020, that generated significant attention in both scientific circles and popular media, has revealed that these songs exhibit statistical patterns that are characteristic of human language. Researchers applied methods originally developed for studying how human babies learn to segment speech into words, techniques based on analyzing the statistical relationships between sequential sounds, and they found that humpback songs show the same kind of underlying structure that human languages show. Human languages follow a particular distribution of word usage called the Zip distribution, named after the linguist George Zip, who first described it. In this distribution, a small number of words are used very frequently, a moderate number are used occasionally, and a large number are used rarely. The most common word in English, the, accounts for about 7% of all words in typical text. The second most common, of, accounts for about 3.5%. The third most common, and, about 3%, and so on, following a mathematical power law. Humpback whale song units follow this same distribution. A small number of unit types appear very frequently in the songs, are repeated often, form the core of many phrases. A moderate number appear occasionally, and a large number appear rarely, perhaps only once or twice in a season. This distribution facilitates learning and memory. It's easier to learn and remember a system where some elements are common and others rare than a system where all elements appear with equal frequency. The common elements provide anchoring points, repeated patterns that help learners recognize structure. The rare elements add richness and complexity without overwhelming the learner. The songs also show what's called small world network structure, a particular way of organizing elements that's found in human language, birdsong, and various other complex systems. In a small world network, most elements are connected to a few neighbors, but some elements serve as hubs, connecting to many others. This creates a system where you can get from any element to any other element through just a few steps, and where the system is robust to damage, because there are multiple pathways between elements. Humpback whale songs have this structure. Most sound units appear in only a few contexts, combined with only a few other units, but some units are more flexible, appearing in many different phrases and themes, serving as connecting elements that link different parts of the song together. These findings suggest that humpback whales are not just making beautiful sounds, but are engaging in a form of communication that shares fundamental similarities with human language. Not in terms of what the songs mean, which remains largely mysterious, not in terms of having words and grammar, the way human languages do, but in terms of how the songs are structured and learned. The songs have syntax, a set of rules or patterns governing how units can be combined. They have cultural transmission, passing from generation to generation, through learning rather than genetic inheritance, and they have the statistical properties that make complex information systems learnable and memorable. Whether humpback songs encode specific meanings, whether they convey detailed information about the singer's identity or location or intentions, whether they function more like music than language, expressing emotion or aesthetic qualities rather than specific content. We don't yet know, but we know they're not simple or random. They're sophisticated, structured, and culturally evolved. Products of intelligent minds grappling with the challenges of communication in a complex social and acoustic environment. Let's shift our attention now to sperm whales. Those deep-diving giants with the largest brains of any creature that has ever lived. Brains that weigh up to 9 kilograms, 6 times heavier than a human brain. Sperm whales are highly social animals, living in tight-knit family groups called units, which consist of females and their offspring. Females remain in their natal unit for life, forming bonds that can last decades. Multiple units that share similar vocal traditions associate with one another to form clans, larger groupings that might encompass hundreds of individuals. Males eventually leave their birth units as they mature, first forming bachelor groups with other young males, then becoming increasingly solitary as they age, though they return to female groups for mating opportunities. Communication is essential for maintaining these social structures, for coordinating movements and activities, for recognizing group members, for passing on cultural knowledge, and sperm whales have developed a rich and nuanced vocal repertoire based on patterns of clicks called codas. A coda is a brief sequence of clicks, usually just a fraction of a second to a few seconds long, with a specific rhythm that makes it recognizable. Unlike the echolocation clicks that sperm whales use for hunting, which are regular and rapidly produced, codas have distinctive temporal patterns, with clicks grouped and spaced in characteristic ways. Early research on sperm whale codas, work conducted in the 1980s and 1990s, focused on categorizing them by the number of clicks and the timing between clicks, creating a kind of catalog of coda types. A common coda pattern, one that appears frequently in many recordings, is the 1+1+3, where the first 2 clicks are evenly spaced, separated by perhaps half a second, followed by 3 more rapid clicks in quick succession. When you listen to it, it sounds like click, click, click. Another common pattern is the 5 regular, 5 evenly spaced clicks with equal intervals between them, like click, 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 click in steady rhythm. Different sperm whale clans, different cultural groups of whales have different coda repertoires, different sets of coda types that they produce regularly and that distinguish them from other clans. Clans that overlap geographically, that swim in the same waters and might encounter one another, can be distinguished by their codas alone, by the types they produce and the relative frequencies with which they produce them. It's analogous to how different human language groups can live in the same region, like French and English speakers in Canada, maintaining distinct linguistic traditions that mark group membership. These coda dialects serve as acoustic badges of clan identity, allowing whales to recognize whether a calling individual belongs to their clan or to a different clan. Information that could be important for deciding whether to approach an affiliate or to avoid. In 2020, 4 researchers working with Project SETI, the Cetacean Translation Initiative, made significant breakthroughs in understanding sperm whale codas by using artificial intelligence and machine learning to analyze thousands of recordings in ways that would be impossible for human researchers processing the data manually. They discovered that codas have far more structure than had been previously recognized, far more dimensions of variation than just the number of clicks and basic timing. Beyond the click count and interclick intervals, sperm whales control tempo, how fast or slow the overall coda is produced. They control rhythm, the specific pattern of emphasis and timing within the coda. They manipulate something the researchers called rubato, borrowing a musical term for the flexible speeding up or slowing down of tempo within a piece. And they add ornamentation, extra clicks or modifications to the basic pattern that add complexity and variation. These features are systematically varied and appear to be controlled deliberately by the whales, rather than being random variations or artifacts of recording conditions. They're also imitated across individuals, with whales in conversation matching each other's coda features in ways that suggest active listening and response. A kind of vocal turn, taking where one whale's coda influences how the next whale produces its coda. This back and forth, this matching and response, resembles the vocal exchanges in human conversation, where speakers adjust their speech patterns to match their conversational partners. A phenomenon known as accommodation or convergence. Even more recently, in late 2020, 4 scientists made another remarkable discovery about sperm whale codas, finding that they contain something remarkably similar to vowels in human speech. The researchers removed the silent gaps between clicks in recorded codas and sped up the recordings, compressing them in time. And when they did this, patterns emerged that looked and sounded like vowel formants, the resonant frequencies that distinguish one vowel sound from another in human language. When we produce vowels, we shape our vocal tract, the space from our larynx through our throat and mouth, and this shape creates resonances at specific frequencies. The pattern of these resonances, which frequencies are enhanced and which are suppressed, determines which vowel we hear. An ah sound has a different formant pattern than an ee sound, even though both are created by vibrating vocal cords at similar fundamental frequencies. Sperm whales appear to produce at least 2 distinct vowel-like sounds in their codas, patterns that the researchers labeled as analogous to the human vowels ah and e. Within a single coda, all the clicks typically have the same vowel quality, creating discrete categories rather than a continuous spectrum. A coda might be entirely ah type or entirely e type, but rarely mixed. The whales also produce diphthong-like sounds, patterns where the formants rise or fall across the duration of the coda, analogous to how the sound glides in English. Diphthongs like the vowel sound in boy or how. These vowel-like patterns are not artifacts of the recording equipment, not random variations caused by the whale's movement through the water or changes in depth or head angle. They're structured, discrete, and consistently distributed across different whales, different contexts, different recording systems. They appear to be deliberately produced features of the codas, acoustic qualities that the whales control, and that might carry information. The discovery suggests that sperm whale communication may have a phonetic structure, a set of distinct acoustic building blocks that can be combined in different ways to create different messages. analogous to how human languages combine consonants and vowels to create words. If this is true, if sperm whales really do have something like a phonetic alphabet, then the information carrying capacity of their communication system could be much larger than previously estimated. Instead of just a few dozen coda types distinguished by click number and basic timing, there could be hundreds of distinct acoustic signals, distinguished by click number, timing, tempo, rhythm, rubato, ornamentation, and vowel quality. The sperm whale communication system may be one of the most sophisticated in the animal kingdom, rivaling or perhaps even exceeding the complexity of any non-human communication system, yet studied in terms of the number of distinct signals and the dimensions along which those signals can vary. Now let's turn to the orcas, those charismatic black and white predators, the largest members of the dolphin family, animals that have captured human imagination for decades through their spectacular acrobatics, their sophisticated hunting techniques, and their apparent intelligence. Orcas live in matrilineal groups called pods, social units centered around a female and her offspring. Sons stay with their mothers for life, an unusual pattern in mammals where males typically disperse. Daughters also remain closely associated with their birth families, though they may swim more independently. This creates stable multi-generational family groups, where grandmothers, mothers, and offspring swim together, maintaining bonds that can last for decades. The most striking feature of orca communication, the aspect that first alerted researchers to the sophistication of their social and cognitive abilities, is the existence of dialects. Each pod has its own distinct set of calls, typically 7 to 17 discrete call types that are produced frequently and form the core of that pod's vocal identity. These calls are not innate, not genetically programmed. Orca calves are not born knowing their pod's dialect. Instead, they learn it over several years by listening to their mothers and other pod members and gradually learning to imitate those sounds. This process of vocal learning begins before birth. Orca calves can hear while still in the womb, and recordings from pregnant females show that the sounds of the mother's pod, the calls and whistles of family members, penetrate into the womb and are audible to the developing fetus. So the learning begins early, with the calf becoming familiar with the acoustic environment of its family before it's even born. After birth, newborn orcas produce high-pitched, rambling vocalizations that don't resemble mature calls, baby babble analogous to the babbling of human infants. By about 2 months of age, they start producing sounds that more closely match adult patterns, though still imperfect. Between 2 and 6 months, their repertoire expands rapidly as they practice and refine their calls. By the time they reach puberty, several years old, they've largely mastered their pod's dialect, though subtle learning and refinement may continue into adulthood. The learning process involves not just producing sounds, but listening carefully to others and adjusting one's own vocalizations to match. It requires auditory memory to remember what calls should sound like, motor control to reproduce them accurately, and feedback mechanisms to compare what you produced with what you intended. The fact that orcas can do this, that they're capable of flexible vocal learning, rather than just producing innate calls, places them in an elite group of species that includes humans, some primates, songbirds, parrots, hummingbirds, bats, elephants, and a few others. Vocal learning is relatively rare in the animal kingdom, requiring specific neural pathways and cognitive abilities, and its presence in orcas underscores their intelligence and neurological sophistication. As we settle deeper into this exploration, our breathing slow and regular, our bodies fully relaxed, we turn now to perhaps the most profound aspect of our journey: the psychology of whale minds, the emotional depth and cognitive sophistication that underlies all of this remarkable communication. The brains of whales are extraordinary structures, not just in size but in organization and complexity. We've mentioned that sperm whales have the largest brains ever to evolve, but size alone doesn't tell the whole story. The structure matters, the types of neurons present, the connections between brain regions, the relative development of different areas, the cerebral cortex, the outer layer of the brain associated with higher level thinking, consciousness, and complex cognition, is highly convoluted in whales, folded into deep grooves and ridges that increase surface area. This convolution, measured by a metric called the gyrification index, is more elaborate in some whale species than in humans. Orcas, in particular, show cortical folding that's more complex than our own, suggesting their brains can pack more neural tissue into a given volume, potentially supporting more complex processing. Perhaps most significantly, whale brains contain specialized cells called spindle neurons, or von Economo neurons, named after the neuroanatomist who first described them in detail. These are unusual neurons, long and spindle-shaped rather than having the typical branching structure of most neurons. In humans, spindle neurons are concentrated in brain regions associated with social cognition, emotional awareness, and empathy, particularly in areas called the anterior cingulate cortex and the frontoinsula. They're thought to be involved in rapid, intuitive judgments about social situations, allowing us to quickly assess others' emotions and intentions, to feel empathy, to make split-second decisions about how to respond in complex social contexts. For many years, spindle neurons were thought to exist only in humans and great apes, considered a unique feature of our lineage. Their discovery in whale brains in the early 2000s was revolutionary, forcing a reevaluation of cetacean cognition and emotional capacity. Not only do whales have these cells, but they appear to have had them for far longer than primates. The whale lineage may have possessed spindle neurons for at least 15 million years, compared to only a few million years in the human lineage. And some whale species, particularly the larger toothed whales, have approximately 3 times as many spindle neurons as humans do, distributed across a larger area of cortex. The presence of these cells, combined with extensive observations of whale behavior in the wild and in captivity, strongly suggests that whales experience complex emotions. They appear to feel joy, sorrow, anger, affection, and empathy. They form deep attachments. They grieve losses. They play and experience what seems to be pleasure. One of the most compelling pieces of evidence for whale emotion, a story that captured international attention and touched hearts around the world, comes from observations of an orca known as Taliqua, or by her research designation, J35. In July of 2018, Taliqua gave birth to a calf in the waters off the coast of Washington state. The calf died within half an hour of birth, likely due to malnutrition as the mother hadn't been able to consume enough salmon. Taliqua Kwa then began carrying her dead baby at the surface, pushing it ahead of her as she swam, balancing it on her head, lifting it when it began to sink. This went on not for hours or days, but for 17 days, during which Kwa traveled over 1,000 miles through the waters of the Pacific Northwest, refusing to let her baby go. Her podmates were observed helping her, taking turns supporting the calf's body when Kwa needed to rest or dive to feed. This extraordinary display of grief, this refusal to accept the death of her offspring, revealed an emotional depth that many people had not imagined possible in a non-human animal. As we drift deeper into this exploration, your body growing heavier with each breath, your mind floating peacefully on these currents of knowledge about whale intelligence and emotion, we turn now to the practical functions of whale communication in their daily lives. We've seen how they make sounds, what those sounds are like, and the remarkable intelligence and emotional depth that underlies their vocal exchanges. Now let's discover what whales actually use these abilities for, how communication helps them survive in the challenging environment of the ocean, how it helps them find food and raise their young and navigate vast distances and maintain the social bonds that give meaning to their lives. One of the most fundamental functions of whale communication, perhaps the most essential for their survival, is navigation. The ocean, as we've explored, is largely featureless to our visual sense. Water extends in all directions without the landmarks we rely on, without mountains or rivers or roads to guide us, without visual references to tell us where we are or which direction to travel. A whale swimming in mid-ocean might be hundreds or thousands of kilometers from the nearest coastline, surrounded by water that looks the same in every direction. Yet whales migrate with remarkable precision, returning year after year to the same feeding grounds, the same breeding areas, traveling thousands of kilometers, and arriving at specific locations at specific times. How do they navigate without maps or compasses, without GPS satellites or written directions? Sound provides at least part of the answer. To a whale's ears, the ocean is full of acoustic features, distinctive sound patterns that mark specific locations or regions. Underwater mountains called seamounts, rising from the abyssal plain to within a few hundred meters of the surface, have characteristic acoustic signatures, sound waves bouncing off a seamount, reflecting from its slopes and peaks, create echoes and reverberation patterns that differ from the flat seafloor. A whale producing low frequency calls and listening to how those calls echo can detect the presence of a seamount, even one that's kilometers away, even one it cannot see through the dark water. Continental shelves, where the ocean depth changes from shallow coastal waters just a few hundred meters deep to the deep abyss of 3,000 or 4,000 meters, create acoustic boundaries where sound behaves differently, where the change in depth affects how sound propagates. The deep ocean has thermal layers, thermoclines, where temperature changes rapidly with depth, and these layers affect sound speed, creating channels and barriers that give different regions distinctive acoustic characteristics. Whales appear to use these acoustic features to navigate, building mental maps, not of what places look like, but of what they sound like, of how their calls echo, of what background sounds are present, of how the acoustic environment feels. A blue whale might remember that a particular seamount produces a specific echo pattern when it calls, that the water near that seamount has a particular temperature structure that creates a characteristic sound channel, that the currents in that area produce specific patterns of background noise. When it hears that combination of features, it knows it's near that seamount. By moving from one acoustic landmark to another, by swimming toward familiar sound patterns and away from unfamiliar ones, a whale can navigate across thousands of kilometers of sea, following its mother on early migrations. Researchers using the United States Navy's underwater listening system, the SOSUS network of hydrophones, originally deployed during the Cold War to listen for Soviet submarines, have tracked singing whales moving through the North Atlantic and found patterns that support this idea of acoustic navigation. They've observed whales swimming directly toward distant seamounts that are hundreds of kilometers away, too far to be detected by any sense except hearing. The whales aim for these features as if following a known route, and when they reach them, they often change course, heading toward a new feature in a different direction, as if they're traveling from waypoint to waypoint along an acoustic roadmap. The whales must have acoustic memories, remembered sound patterns associated with geographic locations, stored information about what different places sound like that allows them to recognize where they are based on what they hear. This acoustic navigation may be particularly important during migration. During those long journeys between feeding and breeding areas, many whale species undertake extraordinary migrations, traveling thousands of kilometers between cold, productive waters, where they feed, and warmer tropical or subtropical waters, where they breed and give birth. Gray whales migrate from the Arctic waters off Alaska, where they feed on bottom-dwelling crustaceans in the shallow seas of the Bering and Chukchi, down the entire west coast of North America to the lagoons of Baja California, where they give birth and nurse their calves in protected waters. This journey covers roughly 16,000 kilometers round trip, making it one of the longest migrations of any mammal. Humpback whales migrate from Antarctic feeding grounds, where they gorge on krill during the southern summer, to tropical breeding areas near Australia, or near islands in the Pacific, or along the coast of South America, crossing entire ocean basins, traveling thousands of kilometers through open ocean with no visible landmarks. These migrations are remarkably precise, with whales returning to the same relatively small feeding areas and breeding grounds year after year. Humpback whales tagged in breeding areas off Hawaii have been photographed in specific feeding areas off Alaska, showing that individuals return to the same locations with extraordinary fidelity. This precision suggests sophisticated navigation abilities. And while whales likely use multiple cues, including Earth's magnetic field, which they may be able to sense, sun position, which could provide directional information, and possibly even the smell or taste of water masses, which differ in their chemical properties, sound almost certainly plays an important role. Low-frequency calls from other whales could act as acoustic beacons, helping migrants orient toward their destinations. If whales already at the feeding grounds are calling, new arrivals could follow those sounds, homing in on the acoustic signature of the feeding area, the characteristic sound patterns of different regions, the way local currents and seafloor features affect the acoustic environment, could help whales recognize when they've reached familiar waters, when they've arrived at the places they remember from previous years. And young whales, making the migration for the first time, might follow experienced whales, learning the route by staying close to their mothers or other pod members, listening to the calls of the group, building their own acoustic maps through social learning and direct experience. Another crucial function of whale communication is coordinating feeding, working together to find and exploit food resources more effectively than any individual could alone. Many whale species feed cooperatively, using teamwork and coordination to concentrate prey or improve hunting efficiency. Humpback whales, as we've mentioned, use bubble net feeding, one of the most spectacular examples of cooperative hunting in the ocean. A group of whales, sometimes just 3 or 4 individuals, but occasionally a dozen or more, works together to trap fish. One or more whales dive beneath a school of fish and begin swimming in an upward spiral, releasing a steady stream of bubbles from their blowholes as they rise. The bubbles form a cylindrical wall, a curtain rising toward the surface, and the fish, confused and frightened by the bubbles, cluster together in the center, forming a concentrated ball of prey at the surface. Before the whales execute the final lunge, before they all surge upward with mouths wide open to engulf the concentrated fish, they produce specific vocalizations called feeding calls. These are long sounds, 5 to 10 seconds in duration, of nearly constant frequency, powerful calls that must be audible to all participants, even if they're separated by dozens or hundreds of meters. The exact purpose of feeding calls isn't fully understood, and researchers continue to debate their function, but they may serve to synchronize the whale's movements to ensure that all participants lunge at the same moment for maximum efficiency. A premature lunge by one individual might scatter the fish before others are ready. A delayed lunge might mean missing the opportunity as the fish begin to escape. By producing these calls at a specific moment, the whales may be coordinating their final approach, saying in effect now, all together, ensuring that the entire group lunges simultaneously. Or the feeding calls may serve a different purpose, helping maintain the group's cohesion during the complex maneuvering required for bubble netting. The whales must swim in formation, must maintain their positions relative to one another, must all contribute to the bubble curtain, and all be ready to lunge when the moment comes. The calls might function as contact signals, ways of announcing presence and position, keeping the group aware of where each individual is located in the 3-dimensional space beneath the waves. Whatever their precise function, the feeding calls are clearly an integral part of the bubble net feeding behavior, part of the coordinated teamwork that makes this hunting strategy so effective. Blue whales also produce distinctive calls associated with feeding, vocalizations that appear to play a role in exploiting krill patches. When blue whales locate a dense concentration of krill, those massive swarms that can turn the water red with their sheer numbers, they produce what researchers call D-calls, those downswept tones that fall in frequency over their duration. These calls may function to announce the discovery of food to other blue whales in the area, attracting them to the rich feeding site. Since blue whales feed by engulfing huge volumes of water, expanding their throat grooves to create a massive pouch that can hold up to 90 tons of water and krill, then contracting muscles to push the water out through their baleen while retaining the krill. They don't compete directly for individual prey items, the way a pack of wolves might compete for a single deer. Instead, multiple blue whales can feed in the same area without interfering with one another. significantly. And there may even be benefits to feeding together. The whale's movements through the water, their lunge feeding creating turbulence and currents, might stir up the krill and concentrate them into denser patches, making them easier to catch. Or the presence of multiple whales might keep the krill from dispersing, with the prey trapped between multiple feeding whales and unable to escape. If these benefits exist, then it would make sense for whales who find good feeding to call to others, to recruit them to the area, creating a mutually beneficial feeding aggregation. Sperm whales diving deep to hunt for squid in the cold darkness, a kilometer or more below the surface, use echolocation to find their prey, those powerful clicks bouncing off squid bodies and returning as echoes that reveal location, size, and movement. But they also produce codas during and between dives, during the social periods when they're resting at the surface or swimming slowly, and these codas may help coordinate the hunting activities of different individuals in a social unit. When one sperm whale finds a productive hunting area, a depth zone or location where squid are abundant, its calls might attract others, might allow the group to concentrate their efforts where prey is most available. Sperm whales in a social unit often dive at different times, staggering their dives so that some individuals are always at the surface breathing, while others are hunting below. This pattern requires coordination, some way of deciding who dives, when, who stays at the surface to babysit calves, when to move to a new area. Codas exchanged between individuals may provide the communication needed for this coordination. Orcas, hunting in coastal waters and open ocean, rely heavily on communication for coordinating their sophisticated hunting strategies. We've discussed how different orca populations specialize in different prey and use different vocalizations in different contexts. Resident orcas that hunt salmon tend to be quite vocal during hunts, producing frequent calls as they search for and pursue fish. The calls likely help the pod stay coordinated as they spread out over several kilometers, with some whales driving fish toward others, with the group working together to herd salmon into tight balls that are easier to catch. The acoustic contact allows them to maintain coordination, even when they can't see one another, even when individuals are separated by distances too great for visual signals. Transient orcas that hunt marine mammals, seals and sea lions and porpoises are much quieter during hunts. Their prey can hear well underwater and might be alerted by vocalizations, might flee or take defensive positions if they hear orcas approaching. So transient orcas often hunt in near silence, producing only occasional quiet clicks for echolocation, relying on visual coordination when they're close together, using their intelligence and experience to anticipate each other's movements without needing to vocalize. This demonstrates a sophisticated awareness of their acoustic environment, an understanding that being heard could compromise a hunt, and the flexibility to adjust communication strategies based on context, to be loud when it's advantageous and silent when stealth is required. Perhaps the most emotionally resonant function of whale communication, the one that touches us most deeply when we contemplate it, is in mother-calf bonding and the rearing of young. When a calf is born, emerging into the water after a gestation period of 10 to 18 months, depending on the species, the mother begins a process of vocal education that will last for years, a patient teaching of the communication skills the calf will need to survive and thrive in its social group. Orca mothers, as we've discussed, produce their pod's distinctive calls more frequently after a calf is born, providing repeated models for the youngster to learn. Emphasizing family-specific calls that mark pod identity. The calf, initially producing random squeaks and squawks, baby babble that bears little resemblance to adult calls, gradually shapes its vocalizations to match the mother's calls, learning through imitation and practice over months and years. Mother whales use calls to stay in contact with their calves, to maintain the bond that's essential for the calf's survival during its vulnerable early months and years. A mother humpback whale, surfacing to breathe while her calf is underwater, might produce a call that the calf responds to, a vocal exchange that allows them to maintain acoustic contact even when they can't see each other. In murky coastal waters where visibility is measured in meters, or at night when darkness makes visual contact impossible, or when diving to depths where light doesn't penetrate, this acoustic contact is essential for keeping mother and calf together. A calf that loses contact with its mother faces grave danger, unable to nurse, vulnerable to predators, lost in the vastness of the ocean. Sperm whale mothers, diving deep to hunt for squid while leaving calves at the surface with babysitters. Other females who guard the young while the mothers hunt produce codas when they return from their dives. These codas may help mothers relocate their particular offspring among other calves in the social unit, may help them announce their return and re-establish contact. The calves, in turn, produce codas that might help mothers identify them individually, that might communicate needs or emotional states, hunger or distress or contentment. The details of this mother-calf communication are still being studied, still being decoded by researchers, but the importance of vocal contact for maintaining the bond is clear. The communication between whales serves so many purposes, so many overlapping functions in their daily lives. It helps them navigate, following acoustic landmarks across thousands of kilometers of ocean. It helps them find and exploit food, coordinating cooperative hunts, announcing the discovery of prey, maintaining group cohesion during feeding. It allows mothers to bond with and educate their young, teaching them the vocalizations they'll need to function in their social groups. It facilitates mating, helping solitary individuals find partners across vast distances, allowing males to compete and females to choose. It maintains social bonds, keeping pod members connected, allowing groups to coordinate movements and activities. It conveys emotional states, expressing joy or distress or excitement, and underlying all of this, making all of it possible, is the intelligence and emotional depth we explored earlier, the complex minds that can learn and remember and feel. But even as we marvel at this acoustic complexity, at the sophistication of whale communication and the intelligence it reveals, we must confront a sobering reality, a challenge that threatens to disrupt or destroy these remarkable systems. The ocean is getting louder, filled with human-made noise that threatens to drown out the voices of whales, to interfere with their ability to hear one another, to navigate, to find food, to maintain the social connections that define their lives. This brings us to the final part of our journey, a look at the threats facing whale communication and what's being done. What can be done to protect these remarkable acoustic beings? The Industrial Revolution brought many changes to the ocean, transforming it from a wilderness barely touched by human activity to an industrialized space crossed by shipping lanes, dotted with oil rigs, traversed by research vessels and military ships. But one of the least visible and most pervasive changes, one that's only been fully appreciated in recent decades, is noise. Ships large and small, from supertankers carrying oil or cargo across the oceans, to fishing boats working coastal waters, to recreational vessels cruising for pleasure, create continuous low-frequency, rumbling as their engines throb and their propellers churn through the water. Each ship is a source of noise, and with tens of thousands of ships at sea at any given time, the cumulative effect is enormous. Offshore oil and gas exploration involves seismic surveys that produce extraordinarily loud, impulsive sounds. Sharp bangs repeated every few seconds for days or weeks as survey vessels crisscross the ocean. Mapping undersea geology. Arrays of air guns are towed behind ships, and every few seconds the air guns fire, releasing compressed air that creates a powerful pressure wave. These waves penetrate the seafloor, reflecting off geological layers deep beneath the surface, and the reflections are recorded by hydrophones to create three-dimensional maps of undersea structures that might contain oil or gas. But these same waves propagate horizontally through the ocean, creating noise that can be detected hundreds of kilometers away. Naval sonar systems, designed to detect submarines by sending out pulses of sound and listening for reflections, project powerful sound into the water at frequencies and intensities that can affect marine mammals. Mid-frequency active sonar, used by many navies, operates at frequencies that overlap with the hearing range of many whale species, and at source levels that can cause disturbance or injury. Offshore construction, pile driving for wind farms and oil platforms and other structures, creates repetitive hammering sounds, sharp impulsive noises, repeated hundreds or thousands of times as pilings are driven into the seafloor. Recreational boating adds higher frequency noise in coastal areas, the whine of outboard motors and the rumble of inboard engines, creating a sonic backdrop in bays and near shore waters that were once relatively quiet. All of this sound has increased the ambient noise level of the ocean dramatically over the past century, particularly in the low-frequency range, below a few hundred hertz, where ship noise is most intense. Researchers estimate that in some frequency ranges, in some ocean regions, the ambient noise level is now more than 12 decibels, louder than it was in the mid-20th century, before the explosion of global shipping that accompanied post-war economic growth. Since the decibel scale is logarithmic, each 10 decibel increase represents a 10-fold increase in sound intensity. A 12 decibel increase means the ocean is roughly 15 times louder than it was, and every decade, in many areas, the noise is roughly doubling as shipping traffic increases, as more ships ply the seas, as engines grow more powerful. For whales that evolved over millions of years in a relatively quiet ocean, where their calls could travel hundreds or thousands of kilometers, where the acoustic environment was dominated by natural sounds, the waves and rain and geological processes and the calls of other marine life. This rising tide of noise is catastrophic. The most direct effect is masking, the covering up of wanted sounds by unwanted noise. Just as you struggle to hear someone speaking to you in a noisy restaurant, just as the babble of other conversations and the clatter of dishes and the background music all interfere with your ability to understand the words of the person across from you. Whales struggle to hear each other against the background of ship noise and seismic surveys, and all the other sounds of human activity. Studies of humpback whale communication have quantified this effect. Researchers measuring the detection range of humpback calls in natural conditions, in wind-dominated noise, found that low-frequency calls could be heard by other whales up to about 4 kilometers away. But when vessel noise was present, when ships were passing through the area creating low-frequency rumbling that overlapped with the frequency range of the whale calls, the detection range dropped to about 2 kilometers. The communication space, the area over which a whale could be heard by others, was cut in half for high-frequency humpback vocalizations. The reduction was even more severe, shrinking from about 2.5 kilometers in natural conditions to only 1 kilometer in vessel noise. This doesn't sound like much, a reduction from 4 kilometers to 2, but the effect compounds. The number of other whales within hearing range is proportional to the area of the communication space, and area scales with the square of the radius. Cutting the communication distance in half means cutting the communication area by a factor of 4. A whale that could previously be heard by perhaps 4 other groups now can be heard by only 1. The size of the potential social network, the number of other whales with whom acoustic contact can be maintained, shrinks dramatically. For species like humpbacks that rely on vocal contact to coordinate movements, to maintain group cohesion, to find mates, this represents a serious disruption of normal behavior. For blue whales and fin whales, whose low-frequency calls are most susceptible to masking by the low-frequency rumble of ships, the impact is even more profound. Researchers have calculated that the area over which a blue whale can communicate today is perhaps only 10 to 20% of what it was before large-scale shipping, before the ocean filled with the noise of engines and propellers. A call that could once be heard across an entire ocean basin, that could travel 1,000 kilometers or more, might now be detected only a few hundred kilometers away. This effectively isolates whales from one another, reducing the chances that widely separated individuals will find each other, will establish and maintain the connections needed for reproduction and social interaction. Whales do try to compensate, do try to be heard over the rising noise. They exhibit what's called the Lombard effect, named after a French physician who first described it in humans. In 1911, the tendency to raise one's voice to be heard over background noise. Just as humans speak louder in noisy environments, projecting their voices to overcome the babble, whales call louder when the ocean is noisy. Blue whale calls have been getting louder over time, increasing in amplitude, and studies using tags attached to individual whales show that they adjust the volume of their calls depending on the ambient noise level. When a ship passes nearby, blue whales call louder. When the ocean is quieter, they return to normal volumes, but there are limits to how much they can increase their volume. Producing louder calls requires more energy, more powerful contractions of the muscles involved in vocalization, more exertion. A whale that must call louder to be heard is expending more resources, burning more calories, and may have less energy available for other essential activities, like feeding or caring for young. And even at increased volumes, the calls may not travel as far in noisy conditions as normal volume calls once traveled in quiet conditions. The whales are compensating as best they can, but the compensation is incomplete, and it comes at a cost. Whales also change their behavior in response to noise. When mid-frequency sonar is activated during naval exercises, blue whales have been observed to stop producing their foraging decalls, going silent even though the sonar is at frequencies far above the range of the whale's own vocalizations. The whales might be avoiding calling because they're stressed by the noise, because the loud, unfamiliar sounds trigger a fear response that inhibits normal behavior. Or they might be stopping because they recognize that their calls won't be heard anyway, that attempting to communicate in such noisy conditions is futile. Or the reasons might be more complex, more subtle, related to factors we don't fully understand. Whatever the cause, the effect is that communication is disrupted. If whales stop calling when there is too much noise, they lose the ability to coordinate, to maintain contact, to share information. The impact on cultural transmission is particularly concerning, particularly troubling when we think about the long-term consequences for these intelligent cultural species. Young whales learn their vocalizations from older whales, listening to songs and codas and dialect calls, and gradually learning to reproduce them, mastering their populations or pods' communication system over months or years of practice and refinement. But if a young humpback whale can't clearly hear an adult's song because ship noise is masking it, because the signal is being drowned out by the rumble of engines, the calf's learning is impaired. The calf might learn a degraded version of the song, missing subtle elements that were masked by noise. Or the calf might take longer to learn, requiring more time and more repetitions before it can accurately reproduce the song. Or it might make more errors, more mistakes in copying, introducing variation that's not intentional innovation, but just failure to hear clearly. Over time, this could lead to the erosion of song complexity, the loss of traditional elements, the breakdown of the cultural traditions that have been maintained for generations or centuries. For orcas, where dialect is a marker of pod identity and potentially important for mate selection, where the dialect defines family and clan membership, noise interference with vocal learning could have long-term consequences for pod cohesion, for social structure, for genetic health. If young orcas can't learn their family's dialect properly, if the precision and distinctiveness of the calls is lost, the dialects might begin to blur together, losing the sharp distinctions that allow individuals to recognize pod members and distinguish them from members of other pods. So what can be done? What solutions exist? What strategies might help protect whale communication from the rising tide of noise? The good news, the encouraging aspect of this challenge, is that noise pollution is potentially more tractable than other environmental threats, like climate change or plastic pollution. Sound doesn't accumulate in the ocean the way pollutants do. It doesn't persist for decades or centuries. If we stop making noise or reduce the noise we make, the ocean becomes quiet again, relatively quickly. Turn off a ship engine, and within minutes, the sound has dissipated. There are several strategies being pursued or proposed to reduce ocean noise and protect whale communication. One approach is ship quieting, designing, and operating vessels in ways that reduce the noise they produce. Modern ship propellers are often designed primarily for efficiency and cost, for moving the ship forward as quickly as possible while burning the least fuel. But they're not optimized for quietness. Propellers that cavitate less, that are designed to minimize the formation of bubbles as they spin are significantly quieter. The bubbles created by cavitation collapse violently, creating noise, and reducing cavitation reduces this source of sound. Slower ship speeds also reduce noise substantially. A ship traveling at 12 knots, moving at a moderate pace, produces considerably less noise than the same ship at 16 or 18 knots, pushing hard. Some shipping companies, responding to pressure from environmental groups and government regulations, have voluntarily reduced speeds in areas known to be important for whales. And these speed reductions have measurable benefits for the acoustic environment, creating windows of relative quiet. Routing ships away from critical whale habitat is another strategy that's being implemented in some regions. If most ship traffic can be moved even a few kilometers away from key feeding or breeding areas, if shipping lanes can be shifted to avoid seasonal concentrations of whales, the noise exposure for whales in those protected areas drops dramatically because sound attenuates with distance. In some regions, including approaches to major ports in North America, shipping lanes have been shifted to avoid whale concentrations, and these shifts have been successful in reducing both noise impacts and the risk of ship strikes, of whales being hit by vessels. The changes require cooperation from shipping companies and regulatory oversight, but they're feasible and they work. Now let your mind rest completely, feeling the weight of all you've learned settling gently around you. Like a soft blanket, you've journeyed through the acoustic realm of whales, understanding how they produce their remarkable sounds, how different species have evolved their own languages and dialects, how their intelligent, emotional minds drive these sophisticated communication systems. You've explored the many functions of whale communication in their daily lives, and you've confronted the challenges they face from human-generated noise. As sleep approaches, perhaps you can carry with you a sense of wonder at these magnificent beings, at the invisible conversations happening beneath the waves, at the songs and clicks and calls that connect whale minds across the ocean's vastness. If you've enjoyed this journey, remember to subscribe to Gentle Sleep ASMR for more explorations. And now drift down into peaceful rest, into dreams that might carry the distant echoes of whale songs, calling you home to sleep. Good night.